So, in today's lecture we will discuss mass transfer in stage wise processes. So, previous lectures we had continuous contact process like packed column. So, two streams are brought in contact whether concurrently or countercurrently. Okay. Now, we have stages. So, these are certain devices, you can think of a mixing chamber, two streams are brought in contact, they spend some time there, then the two streams leave from the stage, they go to the second stage or second device. So, we can have cascades of such stages, all right. And similar to the previous case, we will make a material balance or a species balance on every stage, and we will mark our mole fractions or mass fractions on the equilibrium curves. We will draw the operating curves and we will see what is the driving force of mass transfer at every stages, all right. So, with that introduction, so let us start this stage wise contact process. So, we have stages, two streams are brought in contact for sufficiently long time. Okay, we will see the meaning of this in a minute. What does it mean for sufficiently long time for mass transfer? So, if we give theoretically, if we give infinite time, then we can say that two living streams are in equilibrium, and we will call them equilibrium stage or theoretical stage or ideal stage. Okay. So, all it means two living streams are in equilibrium, okay. And we have given a very long time or infinitely long time. So, we are talking of a device like this, one stream is brought in contact with another stream, this has a mole fractions say x, this has a mole fractions y or x0, y0, here they are uniformly mixed, and when they leave they have the mole fractions x, so we have the mole fraction x1 and the mole fractions of the second stream as y1. So, if they have good mixing here and they have spent a very long time, it is possible that x1 and y1, the two living streams, they will be in equilibrium. So, we can take this, we can take the equilibrium curve like y and x, and we can say that x1 and y1 they are on equilibrium curve. So, this would be y1 and this would be x1. Okay. So, this is the meaning of equilibrium. We have one stage. Now, we can further take this stream and can bring in contact, we can bring in into a second stage, and again we can bring in contact with another stream fresh y0 to show that the living streams again here, and for y0 if we leave it from here they would be in equilibriums. So, this is the meaning of your stages in cascades or in series, etc. So, there are several combinations possible. Okay. We can have cross co-current here or we can have counter current. So, we will see, we will make a material balance on each of these stages. It is possible that there is some other possibility, there is another different type of stages where we have two cascades or two stages in series, then we have two stages in parallels and two streams are getting mixed, etc. So, but for simplicity we will take these two cases here. Okay. So, let us start with cross flow, the most common cross flow cascades. So, we have one stage 1, we have the second stage 2, we have the third stage 3. Okay. Say let us see one stream R with the mole fractions x0 is brought in contact with another stream here which is E, and it has a mole fractions y. Okay. Now, if you recall from our previous lectures, when we had this continuous contact process, we say that it's simpler to work on capital X and capital Y, which is solute free basis. All right. So, we have, if you have binary components, only one component diffuses from one stream to another stream, then it's convenient to work on capital X and capital Y mole fraction as well as a molar flow rate, which is solute free basis, because we realized earlier that operating lines in such cases become linear. So, we can do, so our mathematical computation becomes simpler here. So, we will here also will work on solute free basis mole fractions or solute free molar flow rates or weight mass flow rates. Okay. So, essentially we can write Rs and Es, which is mole per second or kg per second, but it is a solute free basis. So, the transfer component, if it is A in A plus B, we are making a balance on A over B. That is the meaning of your solute free basis. So, Rs x0, it is brought in contact with Es and Y0. Okay. And this stream leaves. Now, if it is Rs, this will remain same as Rs, molar flow rate based on A free B free basis. This will remain the A free basis will remain the same as Rs. Composition will change from x0 to x1, and let us say that this composition changes from y0 to y1, and we have the same flow rate Es here. Okay. So, Rs this will remain the same, Es and Es will remain the same. Of course, the total flow rates will change for both R stream and the E streams. Now, this stream Rs and x1 and with the mole fraction x1, again it is brought in contact with the second stream, say flow rate is Es2 here. So, we can write Es1 here, and this has same mole fractions as earlier y0 for the simplicities. Now, it is important to note that if we have given enough time, residence time or contact time for these two streams Rs and Es in the stage 1, then y1 and x1 they would be in equilibrium. Two living streams will be in equilibrium. Now, this is the maximum we can have separations here, x going from x0 to x1 and y0 to y1 if the two living streams are in equilibrium. Mass transfer will stop here. We cannot have separation more than x1. To have more separations or separation higher than x1 or higher than y1, we have to bring it in the second stage, where again we bring this in contact with the fluids E with the flow rates Es2 with the mole fractions y0. Now, this stream again comes in contact with this stream E, they spend time here, certain time here. Again we can assume that if you have given enough time, the living streams with the mole fractions y1 and the living streams x2, they would be in equilibrium. All right. So, similarly we have x3, we have y0 and we have y3 here. Excuse me, this should be y2. Okay. So, we are following the nomenclatures that the living streams have this suffix, which is number 3, it originates from stage 3. So, we have y2 x2 originating from 2, we have y1 e1 originating from stage 1, and we have the fresh solvents which is y0 and x0 compositions. And since we are working on solid free basis, Rs will remain the same here. We have Es3, the flow rate of the entering into the third stream, and here the flow rate will remain the same as Es3. Okay. Now, what we should do, we should mark these points, the different coordinates on our equilibrium curves or the plots which we had originally. So, now we are again plotting capital Y and capital X, although we can also plot on a small y and a small x, but we have seen the advantages here that if we use capital Y and capital X solid free basis from the stoichiometry, then the operating curves will become linear. So, we have, let us assume that this is our equilibrium curve y versus x, and this is the compositions of starting from x0 and y0. So, let us mark this point as x0 and let mark this point as y0. Okay. Now, if you make a material balance on stage 1, is a very simple Rs x0 minus x1 will be same as will be same as ES1 and Y1 minus Y0. Okay, which means for any stage here, stage 1 and 2, we can also draw this operating curve. So this is nothing but your material balance or species balance which you have made on the transferring component, say A here, between the two entering streams and the leaving streams. So let's mark these points. So if you have x0, y0, there are two ways of doing this. If we know the flow rates of RS and ES1, then we can draw this slope here. It's easier to show that, like to the previous cases, that this will be a negative slope with RS minus RS over ES1. Okay, so this is the slope of the operating curve. And if the streams y1 and x1, the two streams E and RS, they are in equilibrium, then this operating curve will hit here, and we have these compositions y1 and x1. Okay, let's see again here. See, there are two ways of drawing this or plotting this. If the compositions and the specification of the feed RS, X0 and the solvents ES and Y0 they are given, we can mark these 2 points. Okay, if we know the flow rates, we can draw the slope, and we can say that if they have spent enough time, or it's the ideal stages or equilibrium stages, then this line will be on the operating curve. The leaving streams Y1 and X1, they would be in equilibriums. Or given Y1 and X1, if we mark this point, one can connect these 2 points to have this operating curve minus RS over ES1. So it depends upon the type of problems which we have, which is formulated here. Okay. Now when the streams enter 2, again it counters the same compositions Y0, but the flow rates is ES2. All it means, we mark the same point here. This is Y1 and this is your Y0, but now the flow rates, if we assume that ES2 is different from ES1, we will have a different slope here, which will hit here with a difference with a slope of minus RS over ES2. All right, RS is the same here, kg per second, mole per second of the solvent or the carrier gas is the same throughout. So we have RS. However, ES1 and ES2 are different. So we mark this, take the slope and draw all the way till the equilibrium. All it means that the leaving streams Y2 and X2, they are also in the equilibriums. So we have Y2 given in equilibrium with X2. All right, and similarly for the third stage, it has the same composition Y0. Again, with the flow rates is different. At ES3, we have the different slope here, going all the way till Y3, signifying that the two leaving streams are again in equilibriums. So we have Y3 and X3 as an marked on this equilibrium curve here. So we have stage 1, stage 2, stage 3. We starting from X0, we have brought down the compositions till reduced to till X3. Okay, and the more important, say there is an equilibrium curve like this. And also important to note here is that this is very similar to what we had in case of continuous contact process. So in continuous contact process also, if we have two stages, two streams in flowing concurrently, and we give them enough residence time, then the leaving streams will also be in equilibriums. But it's a continuous contact process. So there the operating lines, we can assume that it's a continuous. Here, since we have a stages, right? In one stage, two streams, they come in contact, they spend time, and the leaving streams, they are in equilibriums. All right. Then from the first stage, whatever the streams comes out, if we want to further purify, if we want to further separate the component A, we have to bring in the second stage or second tray, etc., where we bring it in contact with this second solvent Y0. Okay, and therefore we have stage 1, stage 2, and stage 3. If the flow rates are same in all three, flow rates of the E phase, ES1 same as ES2, same as ES3, then the slope, all the three lines will be parallel to each other. So all these three lines will be parallel. That's for the simplicity, etc. And again we want to emphasize here that we are assuming these are the 3, 1, 2, 3, they are equilibrium stages. That means all the living streams are in equilibriums, and their compositions, they fall on this equilibrium curve y x equal to fx. Okay. We would like to do the same things now for counter current cascades. Okay. So, in this case again we have the stages. Now, the stream, one stream enters from first stage, enters the first stage, while the solvent now it enters from the last stage. That is a counter current flow. Okay. Again we can have several stages. So, it is a combination of different stages, cascades, two streams entering counter currently, one from here, and second stream solvent we can call it in the third stage or the NP stage, in arbitrary stage. Then the two stream living streams, again they have a certain residence time and so forth. We can make a material balance and we can mark these points here. Okay. So, let us start this counter current cascade. So, now we have stage 1 and we would like to work still on capital Y and capital X, or the solid free basis flow rates, so that our operating curves are linear. So, we have a stage 1, and now we bring this R 0, small x 0, or we can work on Rs and x 0. Okay. And we have stages like 2, or we have stages like 3, or we have stages say arbitrarily NP. Okay. Only difference is this entering stream R 0, and now we have the entering stream from the other side. So, this is a fresh solvent or fresh E phase, extract phase, we are bringing in the opposite directions counter currently. So, we follow the nomenclatures. This will have a suffix E N P plus 1, and this will have the compositions say Y N P plus 1. If we work on solid free basis, this has a flow rate of E s, and we can say it is a capital Y N P plus 1 like this. So, we have the streams like this, streams like this, and we are following the same nomenclatures. That means, here we can write E s will remain the same as what enters here, and we can use capital Y 1. So, Y 1 means this subscript denotes it originates from stage 1. This means this composition is Y 2 here, this composition is Y 3 here, this composition is Y N P, and its compositions of fresh stream entering the stream is Y N P plus 1, Y N P plus 1. Similarly, these compositions will be capital X 1, capital X 2, capital X 3, and capital X N P. And this flow rate of E s will remain the same throughout, because we are working on solid free basis. However, E N P 2, E N P 3 will vary across these stages, but we said that we are working on the solid free basis for the simplicity. Similarly, R s will remain the same throughout. Now, so here also we can make this overall material balance, but more important is to understand again the equilibriums. Now, let us look at the stage 1. Stage 1, these two streams are entering here with the composition x 0 and y 2, and two streams are leaving here, y 1 and x 1. If we assume that it is an ideal stage, uniform mixing, and they have spent infinite time, then these two streams will be in equilibriums. That means, x 1 and y 1, they can be marked on this equilibrium curve. Similarly, y 2 and x 2 will be in equilibriums, y 3 and x 3 will be in equilibriums, and y n p and x n p, they will be in equilibriums. So, we can mark these 2 points on the equilibrium curves, and if we make a material balance, then all the material balance will give us, given x 1 what is y 2, given x 0 what is y 1, or given x n p what is y n p plus 1. So, let us make a material balance or a species balance for the phase A. We can write R s solid free basis x 0 minus x n p So, we have brought down the concentration mole fractions from x0 to xnp, which is same as species balance ES Y1 leaving stream minus Y NP plus 1. So, ES and RS moles per second or kg per seconds, they are the same. They will remain the same from stage 1 to stage NP, because it is solid free basis. One could have also written on actual flow rates or total flow rates R0, then this should have been R0 x0 minus R NP into small xnp. So, look at the difference now. R0 is different from RNP. However, we work on solid free basis, we can take this RS as a common. Similarly, for this ES, we could have written as E1 Y E1 small y1 minus E, what enters here is NP plus 1 into small y NP plus 1. But if we work on solid free basis, E1 ENP plus 1 can be replaced with ES, and small mole fraction y can be replaced with capital Y and X. The idea is that at any locations, again if we take a stage with y and x, we can draw an operating line which would be linear, y equal to RS over ES x plus ES y1 minus RS x0. So, this is our operating line in a counter current cascades, and important again here is to notice that this is now positive, slope is positive. So, what we noticed here, we have made a species balance for co-current, cross current and counter current cascades, all right, very similar to the previous case where we made a species balance for co-current continuous contact process and counter current continuous contact process. Material balance overall it remains the same. Okay. We have negative slopes in case of co-current or cross co-current, and we had a positive slope in case of counter current flow, counter current continuous contact process or continuous or counter current stage wise processes. However, these are the discrete. We have stage 1, stage 2, stage 3. There we had one continuous column which is a packed bed. All right. Although we are getting the similar mathematical expressions. Now, let us draw or let us mark our points x1, y1, x2, y2 on this equilibrium curves and draw the operating curves. Okay. So, we have the same capital X, capital Y, which is will be equivalent to some small y and small x, different ways of equilibrium curve. So, we can draw say equilibrium curve like this. We have the streams here x0, and we have the streams, corresponding streams in y phase or the E phase as y1. So, we have x0 and y1. This would be the stage 1. Okay. If you recall the previous, we had y1 and we have here x0, and the streams leaving is y1. Okay. So, we mark here y1 x1, and if you look at the operating curves, now it's a linear and a positive slopes. So, we have a linear curve with the slope of plus RS over ES. Okay. And if some equilibrium curve is like this, it's possible that this operating curve may extend to hit this, and we will call this as a pinch. It's a pinch point, right. In case of co-current, if you recall, we had the equilibrium curve like this, and we had the operating curve with the negative slope, which we hits here, it reaches the equilibrium, all right, where we can say that two phases are in equilibriums. Here we have, notice the difference that we have this operating curve which has a positive slope, and still it's possible that in some cases this line may hit equilibrium curves depending upon what type of system we have chosen, and wherever it happens we will have the pinch, zero driving force, and we might require a infinitely not n number of stages here, very infinitely large number of stages. Now, let us get back to this. So, we have marked x0 and x1, and so this is x1 here. Now, we say that y1, this is stream, y1 stream, it's in equilibrium with the stream which leaves here, y1 x1. So if we have y1 here, we have now x1 here. So starting from x0, y1, now we have the second stream which has compositions, two streams, living streams are in equilibrium, so y1 and x1. We can take this x1, get back to the operating curves, which will give us x2 or y2. Again y2 will be in equilibrium with y3, with x2 here. We can mark the x2, get back to the equilibrium curve to mark this point y3, and we have this x3 here. All right. So all we have done, we are saying that we are starting from x0, we have brought down the mole fractions from x0 to x3, and for every time, and we have the streams, other streams where the compositions has changed from y3 to y1. So we had the fresh solvents which was y3, and now the concentration has increased from y3 to y1 here. Okay. We will also like to look at the entire this counter current process slightly different. If you have just one stage and we bring two stages, it doesn't make a difference where are the inlet ports of these two stages, these two streams. So if you have one stage, they can come in contact like this, or they can come in contact like this, or they can come in contact like this. Living streams, if they are in equilibrium, they will be at the equilibrium curve. Okay. All it means, we can also look at every stage. Overall, of course, it's a counter current process. One stream enters here and another stream enters here. This stream leaves from here, this stream leaves from here. But it's possible to draw or to make an analogy with what we had in case of cross co-current flow. So let's look at the slightly different, quite interestingly, this arrangement of counter current. Okay. So we have stage 1, where now we said that earlier we had the entering streams entering like from this sideways. Now all we are saying that let's draw like this. So this is stream which has a composition of x0. Now it enters like this. Okay, and this stream which was living here is like y1. This has a flow rate of Es. Let's draw the second stage, stage 2. Now this is stream which leaves from here, this can go like this, and it can again enter from this stage 2. This stream leaves like this with y2 compositions. Let's draw the third stage. So this is stream which leaves from here like this, again it will enter like this, and so forth. The streams which comes on the top, that extract phase, has a composition y3, and so forth. We have this composition, say y n p plus 1, which we drew here, and this is the compositions of x n p, or x. Here we have this x3 leaving the stage number, this 3, x3 here. Okay, this will also enter some different stages here, which would be marked with NP. Okay. So what we'll notice here, that the composition is x0. Now after this composition is x1. Okay. When it leaves here, this composition is x2. So x0, x1, x2, we have y1, y2, y3. Let's focus on this. Overall, still it's a counter current process. All we have done in one stage, either 1 and 2, we have made a sidewise entries, right? So for one stage or individual stage, still somebody can look at as if it's a stage with a co-current process. Stage, this stream enters with the composition y2, leaves with y1, and this stream leaves with enters x1 and leaves with enters with x0 and leaves with x1. Similarly, we have x1, and this is our x2. So although the overall process is counter current, one stream goes like this and this stream goes like this, individually we can see that still one can treat as stage 1, 2, 3 as a co-current process, which means if you can draw the equilibrium curve of y versus x, with the equilibrium curve given as this. We have earlier we had this operating curve which was plus Rs over Es as a positive for counter current, and we mark those points as x0. Then we had this y1. We said y1 is in contact in equilibrium with x1, so we mark this point as x1. Then we had y2, then we had this as x2, and then we got this as y3. All right. Now this is also possible to treat that since two streams are entering concurrently, we have x0 and y2. So x0, and we have this y2 here, and since the co-current, we can draw the curve like this with the slope of minus Rs over Es. See, we have the same stage like this. Now it enters here, we can draw another stage, one stage, stage 2, and we can have stage 3. In other words, the two ways of representing this counter current. Overall process counter current, we can have this operating curve like Rs by Es. If you look at individually stage 1, 2 and 3, it's possible to draw the lines like minus Rs over Es individually for a co-current process to achieve the same results. Okay. So we have taken two different scenarios. One is a cross co-current and another is counter current stages. We can assume that if these stages are ideal equilibriums or theoretical stages, then the two living streams are in equilibriums. Okay. Now we can solve this problem graphically. We will take an example where we will solve the problem graphically. We will mark these points x0, x1 for different stages, or we can also solve mathematically. That means we can set up the material balance or a species balance for individual stages, stages 1, 2, 3, etc., and we can solve the equations simultaneously. Both will give the same results. In some cases, it is better to work on graphically for our better understanding of the problems. In some cases, when the graphical becomes quite complex, it is better to solve few set of algebraic equations depending upon how many stages we have. If the number of stages are very large, then of course one has to write a code, programming code, Fortran, C, etc., and then one has to solve the compositions or the mass flow rates at every stages here. So before we take up an example, let us take one very special case. So far we drew capital Y versus capital X, and we also said that if you want to work on absolute mole fractions, absolute weight basis, A by A plus B or B by A plus B, there is no harm except that the equilibrium curves and operating curves will not be linear, and then this brings additional computation, etc. So it is always wise to work on the capital Y and capital X, whether it is a contact process or it is a stage wise process. There is a very special case if the equilibrium curves is a straight line. Okay. If it is a straight line, then we can assume that the slope is m. One can make a material balance on every stage with the slope m, constant m throughout for stage 1, stage 2, stage 3. So that we can write y equal to mx, two living streams are in equilibriums. One can obtain a very analytical nice expressions. So we write down these analytical expressions. You can take this example as an exercise and to see whether you get the same result or not. All right. So if we have linear equilibrium curve, like we can write y equal to mx straight line. Okay. Then it is possible to obtain an expressions for number of stages np equals log. As we said that I should take this example as an exercise to solve this or to obtain these expressions. So x0 minus y np plus 1 over m over x np minus y np plus 1 over m 1 minus a plus a, okay, divided by log 1 over a. So this a is called absorption factor. and it's given as RS over MES. So M is slope of the curve. We are assuming it's a linear, it's a constant over the range we are considering. And when we write down this expression, we make a note here that A does not equal to 1. And if A equals 1, then we have this different expression for NP simplified as x0 minus xNP over xNP minus yNP plus 1 over M. And we make a note that this expression is valid or is applicable for R to E phase. All right. So, we are discussing a transfer of components from R phase X to this Y phase, and you should be able to obtain these expressions for this counter current case which we discussed just now. Okay. So, for stays NP, we should be able to obtain. Similarly, if we have transfer from E to R phase, we get slightly different expressions. So, if E to R or Y to X, then we have slightly different expressions for NP log Y NP plus 1 minus M x0 over y1 minus M x0 1 minus 1 over A plus 1 over A over log A, and if here we say that A doesn't equal to 1, and if A equals 1, we have simplified expressions YNP plus 1 minus y1 over y1 minus M x0 if A equals to 1. So, one is like absorptions. Okay. So, we have absorption from gas phase to the liquid phase, and the previous example we had desorption or stripping. Okay. So, we can go to the previous page and we can say that the expression holds good for stripping or desorption. So, X to Y phase. Okay. And this two expressions are known as Kremser Brown Saunders, and the same equations, they have also been given in the textbook in the graphical form. You can have NP, number of stages, and you will see different coordinates, different numbers here, set of curves A or 1 over A, stripping, absorptions in case of absorption or stripping, two different cases when we have mass transfer from E phase to R phase or vice versa R to E phase, and here we have y1 minus mx0 over y np plus 1 minus m x0 or xnp in the second case when we have this stripping y np plus 1 over m over x0 minus y np plus 1 over m. And all right, so this was a very special case where we assume that equilibrium curve is a straight line. So in that case, one doesn't have to make a material balance for every stage, 10 stages, 20 stages. We can use these expressions directly. We have to be careful. The mass transfer is from which to which phase, extract to raffinate, E to R phase or R to E phases. And we have to be careful with the absorption factor A, which we define as RS by MES. If E equals to 1, we notice there is singularity in the equations. So we have to use the simplified equations, second expressions, modified equations, or alternatively we can use the graph given by this Kremser Brown Saunders. So either the equations will work or the graph will work. So what we did earlier, we assume that each stage is ideal or theoretical or equilibrium. All it means, the living streams the coordinates of the living streams will be at the equilibrium. And if certain non-ideality, or if you have not given enough residence time or contact time to the two streams, then the living streams will not be in equilibrium, and these points will not lie on this equilibrium curve. Otherwise, mathematical treatment or the graphical treatment for the two scenarios are the same, whether with equilibrium or non-equilibrium. And all it means, we can define efficiencies, equilibrium efficiencies. So there are very two common efficiencies defined in case of like mass transfer in the stage or mass transfer in the contact process. We have Murphy stage efficiencies, or we define simple efficiencies. So we will have these two definitions here. So let us redraw our equilibrium curve. We had x and we had y. We have this equilibrium curve y and x. Let us draw cocurrent. So we start with P, end with Q, with the slope of minus Rs over Es. All right. So the living streams compositions here is y1, and this is your. So let us mark this is, say this is x1, and the living stream here, the composition is x2. This is your y2. For x1 we have this y1. Okay. Now if they are in equilibrium, then we can extend this line, and we can mark this point as ye. Equivalent to this, we have this xe. So all it means is the maximum separations we can have, which means we can define efficiencies like eta e as y2 minus y1. So this is what we are achieving, y2 minus y1, starting from P and ending with Q here. And what maximum we can achieve is ye minus y1. So all we have done, we extended this line Q to hit this equilibrium curve, from where we get this ye. Similarly, we can define the efficiency based on R phase on this x basis, which should be here equal to x1 minus x2, actual separations over what we have the maximum, we can have x1 minus xe to this. So both efficiencies are defined in case of this stage wise processes or contact process or continuous contact process. One very common efficiency is known as Murphy stage efficiencies, and this efficiencies work very nicely. It works for counter current process, and here one defines E, M, E. Similarly for Murphy efficiencies based on extract phase as y2 minus y1 over y2 star minus y1. So notice the difference. Now we are defining y2 star instead of ye. So all it means, we are saying that whatever we have the x2, we extend this x2. So if you recall from our previous lectures, hypothetical concentrations x2 in equilibrium with this y2 star. Okay. So we are saying that bulk concentration of this phase is in equilibrium with this compositions with the second phase at y2 star. Similarly, we can have E m r as x1 minus x2, and we can have x1 minus x2 star. So given this y2, what maximum we can have in the bulk phase is x star. So of course, you will notice that this definitions is applicable only for counter current process. For co-current doesn't make any sense, because we can never achieve more than ye or xe, etc. So that's why we noted that this Murphy stage efficiency is applicable for counter current process. Okay. There is one small thing here that so far we did is we have flow rates. Okay, so two streams are brought in contact either in a stage or in continuous contact process, co-currently or counter currently, cross currently or counter currently. Okay. It's also possible that we have a batch system. So if you recall from your kinetics, reaction engineering, or in some stoichiometries, now we are talking of two streams or two liquids, say two immiscible liquids, X and Y, L1 and L2, they are brought in contact, we mix them perfectly. So there is no flow rate here. So far we worked on R and E or RS and ES as kg per second, mole per second. Now we are talking of R phase, or the weight of this phase is kg, 5 kg, it's brought in contact with 3 kg of E phase. So no kg per second. and if they are brought in contact for some time T1, T2, T3 or for an infinitely long time, then we separate the two phases again, R and E, and take out the streams from by some decanting process by certain different unit operations. Even in that case, when there is no flow rate or we have the batch process, we can still apply whatever we have done so far. All right. So, all it means, instead of working along the length, now we are saying that we are working along this time coordinates. Okay. So, if we go back and redraw this y versus x, and we are discussing here batch process, still our equilibrium curve will be the same. And now we say that we start with P, certain compositions of one phase as x1 and certain compositions of another phase as y1, and then we spend, and then we have a batch system here. The two phases are brought in contact, they are given enough resistance time, there will be separations, we allow them to settle. Now the curve will still be the same as P going to Q, and the slope of this would be now Rs over Es. Notice the difference, this Es is not kg per second, it is just a kg, and this is your kg. All it means, the movement from P to Q is now on the time instead of on the length. Okay. So, we said that we bring the two phase here, R and E, we give them some sufficient time here, composition changes from say y1 to y2, and if we have this E phase, okay, the composition changes from x1 to x2. Now, instead of length, all we are saying that we are giving them some time t. But if we make a material balance now from initial to final, unlike here we have a steady state, and we say we make a material balance between inlet and outlet. All right. But notice that we will get the same results here. Now, we are drawing P to Q. Now, the compositions here is y2 after certain time, composition here is x2 after certain time. So, we have achieved x1 minus x2 or y1 minus y2, these two difference here over a time t instead of over the length L. Otherwise, our mathematical treatment is same as before. So, whether we have a batch process or we have this continuous contact process or a stage wise etc., material balance or the equation, mathematical form of the equations will be similar. So, it does not matter when we say that two streams are brought in contact at certain flow rates, or they are mixed in a batch reactor or batch adsorber or batch absorber. Okay. It is just a question of working on it, instead of time coordinates, we are working on the length coordinates. We have the similar situations, whether we have a co-current or counter current etc., does not make a difference here. All right. In the next lecture, we will take an example of what we have discussed here in case of cross co-current and counter current processes. All right.